Good afternoon, everybody. My name is Josh Veers. I'm the host for today's CITRIS Research Exchange. I am the campus director at the University of California, Merced for CITRIS in the Banatao Institute. So welcome. This is the 13th year for the CITRIS Research Exchange and Seminar Series. And I know many of you have attended in person in CITRIS Hall, and what a great venue, and certainly a great opportunity to get some in-person lunch. But today, thank you for joining virtually. This is the final talk of the Spring 2021 series. But please be sure to check in and view the website for the Research Exchange for early September and fall 2021. Very conceivable that we'll have some in-person opportunities. And I know that's something that we're all looking forward to as we move forward. So stay tuned for that, and let's look forward to today's talk. So today we're joined by Dr. Samuel Markolf, who's an assistant professor in the Department of Civil and Environmental Engineering at UC Merced. Sam recently joined us. His research broadly focuses on applying systems thinking to sustainability and resilience challenges facing cities and infrastructure systems. Prior to joining UC Merced, he was an assistant research professor at Arizona State University, as well as a research fellow within the NSF-sponsored Urban Resilience to Extremes Sustainability Research Network. And I should also point out that Dr. Markolf's work has been featured by NSF in their new Convergence Thrusts. So certainly something we're all very curious about and gearing our own research toward. Without further ado, it is my great honor to welcome Sam Markolf. It's all yours, Sam.
Great, thank you so much, Josh, and the rest of the CITRIS community. It's a privilege to be here, and I'm very excited to kind of be here as I'm entering my third month at UC Merced and within the UC system. So yeah, I'm very grateful to have the opportunity to share with y'all a little bit about my work, broadly looking at how we can think about infrastructure, sustainability, and resilience in the context of the Anthropocene. And so just to kind of ground everyone a little bit before diving in, given the diversity of backgrounds within the CITRIS community, I erred on the side of breadth over depth for most of this talk, but nonetheless, I'm still very happy to go into more detail on any of the topics that come up, either in the Q&A at the end or offline at a later time. There's kind of two key sections that my talk will be focusing on. First is this one looking at themes of the Anthropocene and their potential implications on infrastructure systems. So this will kind of highlight some of my work that has focused on kind of conceptually framing how these different system dynamics and conditions may be interacting and having implications on our infrastructure systems. And this part is a little bit more on the qualitative side of things. And then the second major section will be a little bit more quantitative, looking at how some different approaches for analyzing infrastructure systems in the context of the Anthropocene with goals of sustainability and resilience in mind. So starting kind of at the highest level, just wanted to kind of introduce the topic of the Anthropocene a little bit. I'm sure most folks have probably heard of it in some form or another at this point. It is becoming a pretty popular term, both in kind of the academic world, but also in more popular media. There's full issues of The Economist dedicated to it. And so there's kind of a wide variety of definitions and meanings associated with it. But what I've included here is kind of my broadest sense of what is meant by the Anthropocene. And it really is just the age of humans. And as best as we can tell, this is kind of the first time in our history where one single species has strong, if not dominant, influence on a wide variety of global processes and systems at a global scale. And so I don't, for the talk today, it's not necessarily important to kind of worry about the exact timing of when the Anthropocene maybe started. We'll briefly touch on that, but or even what the, what's the right or wrong definition. But for our purposes, it's really just kind of this idea that human beings are really driving a lot of global processes at quite a large scale, and that's often kind of depicted by things that we see here in the picture, where previously natural landscapes are often irrevocably impacted by humans, and in particular kind of the socio-technical systems related to humans and their activity. And while these kind of environmental implications are often the focus of any discussion of the Anthropocene, and certainly a big part of my research and thinking about it, I've also started to think a little bit more broadly about kind of what it means to be in the Anthropocene. And so I know these figures are a little hard to read. They're not, you don't necessarily need to know too much about the details, but the main takeaway here is that besides these kind of environmental implications, there's a whole suite of processes and systems really that are kind of exhibiting this similar trends, similar dynamics, really this kind of exponential growth in many cases that we see in a variety of things, ranging from population, the number of motor vehicles, the amount of information that we produce and consume and process on a day-to-day basis, as well as the whole host of environmental factors such as ozone depletion, carbon dioxide emissions, biodiversity, things like that. So the environmental aspects are a key part of the Anthropocene, but more and more I'm starting to think of it more broadly as this kind of just this large accelerating trend in a variety of our social, ecological, and technological systems, and then the kind of dynamics and feedbacks that emerge across those systems are kind of accelerating and becoming increasingly complex, sometimes to the detriment of our even understanding or ability to comprehend what is actually happening within any one of these systems, let alone the kind of combination of the systems. And so that we'll kind of dive into that more as we move along today. And so kind of focusing a little bit more on these broader anthropogenic forcings on our infrastructure systems, and more importantly, the services that they provide. So, we really want to think of infrastructure as providing services and benefits to human beings, so, and the environment. So, the physical infrastructure itself is certainly important to that, but really what's more important is kind of the impacts, the benefits, and often the harms that these systems can contribute to social and ecological systems. And so this is just kind of a schematic highlighting some of these, emergent properties, for lack of a better term, of the Anthropocene, and how they are kind of influencing and starting to influence infrastructure systems and infrastructure services. So, technology is rapidly accelerating and changing. Financial mechanisms are often changing and accelerating. Same with social and cultural aspects. So, what was desirable 5 years ago or even 10 years ago is maybe no longer what's kind of driving current demand implications. Increasingly, political considerations need to be factored in more thoroughly, where you maybe have something like increasing polarization resulting in the support or lack of support for certain types of infrastructure, or the bolstering of infrastructure in certain locations, but not others. And then certainly the increasing embeddedness of cyber technologies and quote unquote smart systems into the more traditional infrastructure systems, is leading to rapid changes in a variety of fronts. So we're not going to touch on all of these in detail, but I just wanted to kind of include that as part of my background section here, and just kind of highlight that there are a number of fronts and places where these dynamics are really starting to intersect with infrastructure systems and infrastructure services, and lead to emergent properties, many times unpredictable outcomes in properties. And so ultimately, this is kind of one of the core questions behind my work, is just how do we wrap our head around all of these interacting and dynamic processes that are kind of on an accelerating pathway. And so before kind of drilling down into three of those kind of emergent properties in a little more detail, I did just want to kind of take a step back and talk a little bit briefly about just kind of how infrastructure is designed and implemented kind of in its most general sense. And here we'll be talking particularly with regards to kind of designing any given infrastructure system for the kind of external climate or environment in which it'll be operating. So often infrastructure have a certain design criteria, or more often design storm criteria to which they are designed. And this can be broadly defined as the maximum acceptable threshold or probability of occurrence of a particular hazard to which infrastructure systems are designed to endure. So you'll often hear terms like, 1 in 100 design storm, or maybe 1 in 50. And so that's just kind of a shorthand that's developed to refer to the type of storm, but more specifically the frequency and intensity of a representative storm. In this case, we're kind of highlighting rainfall, to which a given infrastructure system would be designed to withstand. So just to kind of emphasize that a little bit more, if you set 100 years as your return period, and you're interested in a 60-minute duration for that 100-year storm, you would want to design, in this case for Phoenix, you would want to design your stormwater infrastructure to be able to handle at least 1.97 inches of rainfall for that given design criteria. There are often kind of two types of these design storm criteria. One is what I would call frequency-based. And so that's where the risk is implicitly considered. And by risk, I mean the risk of the design criteria being exceeded, or more severely, the infrastructure failing to prevent against disruptions from a particular hazard. And this design is based primarily on a prescribed recurrence interval. So that's kind of what I just illustrated. So, designing to a 100-year storm event or a 50-year storm event, et cetera. There can also be risk-based design, where the risk of failure is more explicitly considered. So there, your design is based primarily on the possible impacts of failure. And so you would often look at kind of a particular threshold by which you believe your infrastructure will fail, and then you start to think about what are the implications of that failure and what mitigating actions do you need to take. So the frequency-based criteria is one that's more often used, but increasingly we are starting to see a shift more towards that risk-based design. And so this is kind of further highlighted here, where we were looking at kind of an assessment of the various design criteria for different infrastructure systems within Arizona, and not only different infrastructure systems, but different hazards to which they are designed to withstand. And so looking at the water, power, and transportation systems and their design criteria for precipitation, temperature, and wind, we can kind of see that there's a wide suite of practices that are implemented here. For the most part, there are design criteria for a variety of the hazards, but no one infrastructure system that we looked at had design criteria for all three of these hazards. You'll also notice that there is kind of a mix of this return period versus risk-based or threshold approach. And so ultimately the kind of takeaway here is that design storm criteria exists for multiple types of infrastructure and hazards, but there is a variance in the methods used and the degree of robustness across systems. And by robustness, I mean kind of the level of protection. So if it's a return period based approach, a more robust system would be designing to a 100-year storm as opposed to designing to a 50-year storm. And similarly, a more robust threshold-based approach would be designing for wind that has speeds up to 125 miles per hour rather than wind that has speeds up to 75 miles per hour, for example. So we see this kind of mix of approaches, which we would probably want to come to expect. You know, although the different infrastructure types do have overlap and interconnections with each other, which we'll talk about later, they are all kind of operating under their own conditions, so to speak, and so you would kind of expect them to develop the design criteria that are best suited for them. But this also highlights one of the challenges with cross-sector conversations and design. So as we'll talk later about the interconnectedness and growing interconnectedness between transportation systems, power systems, and water systems, one of the key disconnect points is that they aren't often starting from the same kind of design criteria, and therefore it can make it challenging to kind of come up with a unified multi-infrastructure design criteria that could potentially allow for better protections for the suite of systems rather than one system at a time. And then the other important thing to point out here before we transition into the kind of specific themes of the Anthropocene that we'll drill down into further is that regardless of which type of design criteria there is, they are all often based on a common assumption, and that is the common assumption of stationarity. So these design criteria are based on historical data and historical conditions, and given the long-lived nature of most infrastructure systems, the design criteria are put in place with the assumption that the climate that existed based on the historical data is going to more or less be the same as the climate that exists throughout the lifetime of the infrastructure system. And so as we're starting to observe different changes in our climate and model anticipated changes in our climate, we recognize that that assumption of stationarity is likely no longer valid, and that can have some pretty serious implications for how how well our currently implemented and designed infrastructure is likely to hold up to a variety of extreme weather events and natural hazards, and two, raises the impetus for us as kind of the engineering community to really have to regroup and rethink how we want to implement these design criteria moving forward, with the consideration of non-stationarity included in that process. And so just to kind of speak on that a little bit more, on the left-hand side, where you'll start to see more and more of these kind of news articles, as well as academic articles, kind of highlighting some of the breakdowns that we're starting to see in kind of the current design storm process. So, for example, Houston had its third 50-year quote-unquote flood event in a 3-year period. So if you were designing to that 500-year storm event, you would not expect that level of recurrence to be happening. Nonetheless, we are starting to see that happen. And then the graphs on the right here kind of highlight some kind of historical conditions over two kind of separate time periods, one kind of from the earlier part of 1950 to 1975, and then the right-hand side you'll see 1985 to closer to the year 2000, and you can see that a 1 in 100 or 100-year storm event, what that even means is it changes drastically even just across those two separate time periods. So infrastructure that was designed and built, say, in 1965, we would expect that to be perform very different than infrastructure that was designed and implemented in, say, 1990. Even though they're both designed to that 100-year storm criteria, what that would actually end up resulting in and looking like on the ground is going to be very different. And so these figures and even these kind of anecdotal evidence from various media articles really highlight the this idea of climate change and non-stationarity as one of these emergent features of the Anthropocene, and one that we in the engineering community, specifically engineers that work on the implementation and management of physical infrastructure systems, will have to start grappling with. The other kind of, another of these kind of emergent characteristics of the Anthropocene is that our infrastructure systems are increasingly becoming interconnected with one another and increasingly exposed to concurrent hazards. And so this work kind of highlights a conceptual mapping of the implications of these interconnections and how they can manifest in a number of different what we call pathways of disruption. So just to kind of briefly walk you through this figure. So a lot of the focus on kind of infrastructure resilience and even kind of some of the design storm criteria that I previously discussed relates to this direct physical pathway. So there you're kind of looking at the hazards impact on the physical infrastructure. It's kind of what you would probably most quickly think about when you're trying to think of protecting or enhancing infrastructure against various extreme weather events or hazards. And so an example of this would be just the washout of a bridge due to flooding or pavement deteriorating under extreme heat conditions. From there, we can move to direct but non-physical pathways of disruption. And so this regime is kind of characterized by impacts on human health or human behavior and decision-making. And so here you have a hazard that can still lead to some sort of disruption or failure, but the physical infrastructure itself will remain intact. So a good example of this is congestion resulting from extreme precipitation, where the physical infrastructure is fine and holds up. Nonetheless, the service that the infrastructure is still trying to deliver can be disrupted. And there's a really kind of extreme example of this from the city of Atlanta in 2014, when there was kind of a sudden snowstorm that blew through the area. And as people were rushing home to kind of get home from work before the worst of the storm hit, the weather conditions kind of changed rapidly, and multiple people ended up basically getting stranded on the highway for upwards of 12 hours. There was some stories of school buses, children in school buses kind of having to spend the night on the highway. And so again, the physical infrastructure was perfectly fine. This wasn't necessarily a unprecedented snow event. Nonetheless, there was still more or less a catastrophic disruption to people's mobility and their ability to get from point A to point B in a safe and timely manner. From there, we can move to the indirect physical pathway of disruption. And here we see disruptions that result from other interconnected or co-located infrastructure systems. So what has been happening in Texas over the past several weeks is a really clear example of this, where you have sustained outage to power systems, which then kind of cascades over to outages in the water system. And so you kind of lose the ability to treat or pump water. And so the physical infrastructure in the water system is more or less fine. Nonetheless, the loss of power as a key input to that system ultimately, again, still results in the services being disrupted. And then finally, we have the non-physical or the indirect non-physical pathways of disruption. And these are kind of in many ways the hardest to conceptualize or characterize, but we kind of define those as disruptions that result from the loss of information, social assets, financial assets, or other resources. An example of this would be an information communication technology outage that disrupts traffic communication and management, or routing and mapping services. Another example would be kind of with the city of Houston's kind of continual issues with flooding in recent years. Part of that is due to the physical infrastructure itself, but part of that is also due to broader environmental and social factors, such as population growth, increased impervious surfaces, lack of zoning laws. All of those kind of compound with the physical infrastructure to exacerbate some of the flooding problems that they're dealing with. So again, you're kind of moving outside of the technological realm and getting more into the social and ecological realm. And just to kind of illustrate how this conceptual framing can be kind of operationalized, for lack of a better term, if we focus on a transportation system and some of the possible pathways of disruption that can be observed from extreme heat. Here we kind of see some of the main direct physical disruptions that might occur. So ranging from impacts to the vehicles themselves, whether they're personal vehicles or public transportation vehicles, to the infrastructure. So loss of pavement integrity, rails and roads buckling, catenary wire sagging if you have an electrified light rail system, for example. So again, these are the ones that we think about most frequently. These have a lot of attention and literature behind them. But what happens when you start to incorporate the other three pathways of disruption? Your scope really gets blown up here, and you can really see how all of a sudden there's all of these other aspects and dynamics that warrant attention. So obviously, not all these are kind of equally likely to happen or equally probable, but nonetheless, they are all possible. These are all based on kind of a literature review, based on kind of observed impacts to various infrastructure systems. So really the takeaway here is, given the kind of increasing interconnectedness across our infrastructure systems, we can no longer just think of risk in this domain. We really need to start thinking about it in this kind of multi-tier domain. And that creates a series of additional difficulties and complexities, both in terms of just our kind of understanding and comprehension, but also in any type of modeling or mitigation efforts that you might take to try and avoid some of these impacts. And then finally, kind of the third theme of the Anthropocene that I want to touch on and highlight is that not only are infrastructure systems becoming more interconnected, but the infrastructure systems are also increasingly connected and connected to broader social and ecological systems. And so this creates a series of kind of dynamic feedbacks and emergent properties that can sometimes lead to surprising or maladaptive outcomes that we're constantly trying to kind of wrap our head around. So the kind of approach that we use here to kind of first identify and frame these dynamics is a SETS lens. So SETS is an acronym for social, ecological, technological systems. And so really the key idea here is that you know, infrastructure and cities we kind of posit that they should be thought of as sets rather than simply technological systems or socio-technical systems or eco-technical systems. Really to have any chance at trying to fully understand these dynamics and emergent processes, it's incumbent upon us to do our best to try and think across all three of these lenses at the same time. And one of the most impactful outcomes of using the SETS lens is that I found it to be a very useful tool for identifying something like lock-in, which can be defined as constraints on infrastructure today as a result of past decisions and actions, even in light of new operating conditions or alternatives. So to kind of rephrase that, you know, we increasingly recognize the threats and hazards that climate change is posing to our infrastructure systems. However, something like lock-in can actually be a pretty big inhibitor in us actually being able to revise those design criteria or really be able to adapt or alter our infrastructure in a way that makes it easier to prepare for and mitigate some of the impacts of that changing climate. And to illustrate that a little bit more, we have we've done some kind of come up with some case studies. And so I think this is a really nice one that kind of illustrates how this process can play out and how you can ultimately get into this state of lock-in. And so this is kind of an example from the Mississippi River Delta and kind of tracking some of the main SETS dynamics that have played out in that region over the past several decades. And for a little bit of background here, in the 1950s, the Army Corps of Engineers recognized that the main channel of the Mississippi River was increasingly likely to kind of undergo natural variation and essentially split off. And right here where you see it's labeled as the lower Old River, they anticipated that within a few years, the main channel of the Mississippi River would potentially switch from its current channel, which goes through, you know, New Orleans and other places like that, over to what is the Atchafalaya River. And that would, you know, that can have a variety of various natural and social implications, but they're mostly worried about the social implications of that potential shift in the river's course, mainly for the potential loss of you know, economic opportunities for places like New Orleans. And so how they responded was implementing a series of levees, dams, and locks to kind of instill more control over the system. I use control in quotes there. And so that's what happens here. You have this kind of social impetus to install technological solutions to an identified problem. And then those dams, levees, and locks create their own impacts on the local ecological conditions. From there, that kind of increased perception or assumption of control and predictability allows for additional social processes to play out. So more industry can come into the area, more people can move into the area, and things like that. From there, though, more people and more industry that are in place increases the risk or the exposure to any type of potential failure of the dams, levees, and locks. And so that kind of puts you on this feedback loop where there's, again, additional pressure to reinforce, re-armor, double down, so to speak, on the infrastructure that's put in place, which then has further ecological impacts. And you kind of get into this loop where you're increasing the risk, then putting in a technological system in place to modify or reduce the risk, but then that brings more people into the area. And so you kind of get into this feedback loop, and that this is kind of our conceptualization or visualization of that lock-in phenomenon. And so now, really the Army Corps is kind of stuck in this loop where actually the physical river is locked into this 70-30 split between the Mississippi River and the Atchafalaya River. And given all this kind of momentum and subsequent development and inertia that's built up in the system, there's not an easy way to deviate from that, even though we recognize with each passing year and of age and degradation in these dams, locks, and levees, the kind of risk of any type of failure marginally increases. And so even though we know that this is maybe not a tenable situation to be in, we're kind of currently stuck in this loop without really having an easy way to shift our practices or shift our approaches. Okay, so yeah, so that's kind of a quick overview of some of the framing of these key concepts. In particular, focusing on three main kind of emergent themes of the Anthropocene and how they are starting to impact our infrastructure system. So again, that was climate non-stationarity, interdependencies and interconnections across infrastructure systems, and then dynamics across linked social, ecological, and technological systems. So now I want to transition a little bit into the more quantitative portion of my talk and kind of highlight a couple projects where we're actually trying to kind of analyze some of these systems and some of these phenomena. And so just kind of want to give a little overview of some of the different approaches that I've used to do that in the context of the Anthropocene and these emergent factors within the Anthropocene. And so a couple things to highlight here. A key thread for these first three projects is the importance of matching the scale and the scope of your analysis with the scale and scope of the problem. And you know, I think that maybe sounds relatively straightforward, but it's often easier said than done. And in my work, I found it to be a little bit more of an art than a science. And so I think this will be that idea of really developing our ability to find the appropriate data, find the appropriate scale and scope for our problem, whatever it may be, will be increasingly important in the context of the Anthropocene, an increasingly important skill for us to try and develop within our students and within ourselves. And then kind of a related point or related theme shows up in this fourth project here, where not only do we want to try and match the scale and scope of our analysis with the problem, but we also need to try and start matching the complexity of our analysis with the complexity of the problems that we're dealing with. And what I mean by complexity is just sort of these dynamics that I just touched on, the kind of growing interdependencies between infrastructure systems and broader social ecological systems. And two, just the kind of sheer amount of data that we are increasingly exposed to and processing on a day-to-day or second-by-second basis. That is kind of reflecting these broader global themes. And so our AI is increasingly important factor and tool in our toolkit for kind of having that requisite complexity. And so I'll touch a little bit on that, about some of the kind of opportunities and challenges for applying AI to our infrastructure systems. Okay, so first we'll touch on some previous work looking at estimating metropolitan greenhouse gas emissions using ubiquitous data sets. So over the past couple decades, cities have kind of increasingly taken up the mantle as kind of the vanguard for greenhouse gas reduction efforts, at least here in the United States. And that's done in a variety of different ways, but the kind of the most common approach is that cities will set greenhouse gas reduction targets for themselves, where they say, we're going to reduce our emissions by 80% by the year 2050, for example. So this chart kind of is just a quick snapshot of some of the major cities that have developed some sort of greenhouse gas reduction target, and kind of an overview of what those targets look like, both in terms of an overall reduction as well as kind of an annualized rate of reduction that they need to achieve. So this is all well and good, and the cities should definitely be applauded for their effort, especially for kind of, again, taking up this mantle in the absence of really any type of cohesive federal policy in recent years. However, there are a couple challenges that emerge with this effort. So one, to do this effectively, you kind of need to take stock of your emissions or take an inventory of your emissions on a pretty regular basis. So ideally it would be every year, if not every couple of years, just to sort of keep track of yourself and your city's emissions and sort of see how you're doing versus your goal that you set for yourself. So you kind of need to be able to monitor your progress as you move towards reaching your goal. But this can be a very data intensive process, a very resource intensive process. And you know, as we're familiar with, most cities, you know, don't have a lot of resources available to them, both in terms of human capital or actual, you know, monetary capital to dedicate to this effort and this continual monitoring and inventorying effort. So coming up with these regular inventories has actually emerged as quite a challenge for a lot of cities. And then the other thing, kind of getting to that point of you know, the scale and scope of your analysis and your policy, trying to match up with the scale and scope of the problem. Climate change, you know, as we know, is a global problem, a global challenge, and you kind of really need your efforts to start matching that global scale. And so again, this is not to take away from the city's efforts at all, but that kind of a for lack of a better term, you know, city by city approach, lack of coordination across cities often doesn't quite meet the scale and scope that is warranted for a problem like reducing overall emissions, greenhouse gas emissions. And so to kind of emphasize that a little bit more, we can look at this illustrative example of Pittsburgh. So the city of Pittsburgh has set their own, you know, greenhouse gas reduction target, but you know, we're all kind of familiar with the idea, at least prior to COVID, you know, someone may work outside of a city, but live inside of a city, or live inside of a city and work outside of it. So the emissions that can emerge on a day-to-day basis are often not confined to the city limits, but instead are more likely to occur kind of at this regional or this metropolitan scale. Nonetheless, the cities are kind of, you know, they're hindered in their ability to do much at this regional scale. And so their targets are often kind of set and limited to the city limits. So again, we kind of had this scale mismatch problem. So having said all that, we were able to make use of these ubiquitous data sets that are available from a variety of entities like the Environmental Protection Agency and the Energy Information Administration and some of the state agencies as well, to kind of come up with a consistent approach and a consistent data set for estimating metropolitan scale emissions for the 100 largest metropolitan areas in the United States. So this can kind of address those issues in a couple different ways. One, it allows for an apples to apples comparison of one region to another, rather than having to worry about one city using kind of a different methodology from another city to come up with their estimates. ultimately, we're interested in kind of the collective progress or the collective reduction of emissions across the board, rather than one city, any one city. And so this integrated approach allows for that consistent estimation and comparison across these kind of ubiquitous data sets that we're able to integrate and pull from. Also have been around for quite a while, and so this approach also allows us to kind of deal with that inventory issue and the need to kind of have a regular inventory or regular check-in on progress. And so we have now been able to kind of estimate how emissions have changed over the course of the figure here is showing 2002 versus 2014 emissions. But we have even more recent data to that. So now we can really start to kind of get a consistent comparison across roughly a 20-year period. And again, this is all data that's already collected by these various federal and state agencies. The cities don't have to really do much themselves or commit any type of money or resources to coming up with these estimates. Nonetheless, we're able to kind of regularly produce them and update them. And then finally, this also allows for this for us to kind of look at how certain activities or certain geographic scales may be contributing to underreported activities or emissions. And so on the left-hand side here, we can see underreported activities, which here were classified as transportation that's happening outside of the urban core, but still within that metropolitan area, as well as industrial activity that's happening within the metropolitan area. Those can contribute to, on average, 25% of overall emissions, and those are often not incorporated in the kind of the current approach. And then also just kind of looking at that metropolitan scale, as opposed to just focusing on the urban core, you can see on average a 56% difference in kind of what the emissions look like. So overall, this approach allows us to use publicly available data that's to provide reasonable estimates for metropolitan greenhouse gas emissions, and allows us to kind of start matching the scale and scope of our analysis and of the kind of potential policies with the scale and scope of the problem of global greenhouse gas emissions. So next, I just want to highlight briefly kind of some ongoing work that is, instead of going from the kind of scale or using data that's already out there and has been collected kind of on a regular basis, work that is focusing on kind of collecting our own data and making use of kind of sensor-enabled public transportation systems to provide us some additional insights to the air quality and extreme heat exposure that are happening within a metropolitan area. So in particular, we realized that a lot of the kind of current approaches for monitoring and mitigating extreme heat and air pollution occur kind of at this larger county scale and rely on relatively coarse data from stationary monitoring networks. And so that kind of leaves these gaps that are highlighted here in the red circles, where there's kind of large portions of the region that don't really have much monitoring or any monitoring. And oftentimes these areas also coincide with kind of underrepresented communities who may be the most vulnerable communities to exposure to air pollution or extreme heat. And so there's kind of this gap and this need for us to take our monitoring down to the human scale where the actual impacts are experienced. So, if you are taking the bus or the light rail to work or to get around town, you're going to be exposed to these air quality conditions or these extreme heat conditions. And therefore, there's kind of an impetus to try and get monitoring and measurement down at that scale so that transit riders can make more informed decisions policy makers can make more informed decisions about the right mitigation strategies to implement. And so to do this, we are embedding air quality, handheld, relatively inexpensive, battery-powered air quality and temperature sensors onto light rail trains in order to form a mobile platform for collecting, sharing, and analyzing this temperature and air quality data at a higher temporal and geographic resolution than it is currently being measured by those kind of county level monitoring stations. And so this is very much ongoing. We have just kind of done our first couple trial runs with getting the sensors attached to the light rail. And over the next several months, we'll really start to do our kind of data collection. But this is kind of a schematic of what we anticipate some of the results to potentially look like. And so ultimately what we're expecting is we'll have this high resolution temperature and air quality measurements that can help us identify these localized hotspots for poor air quality or for higher than expected temperatures, and therefore we can start to inform decisions by the writers and by the policymakers for either putting in additional monitoring stations or mitigation strategies that can be used to kind of reduce the risk of the people living and coming in contact with these hotspots. Another kind of ongoing effort here is looking at kind of modeling the potential implications of disruptions to intercity transportation networks. So the previous two projects kind of highlighted either using data that's already out there in kind of an integrative way, or coming up with new approaches for collecting data that we view as kind of needed at a kind of useful scale. We also need to start taking a more of an anticipatory approach for various disruptions and things that we cannot necessarily experiment with or observe kind of on a regular basis. So we can't necessarily, we don't really want to be in the habit of observing various disruptions. We also want to be able to kind of anticipate them and hopefully prevent them before they happen. And so that's where kind of modeling efforts can come into play. And so ultimately what we're doing here is combining various approaches. So using kind of network modeling with agent-based modeling to be able to assess traffic and travel impacts of various simulation scenarios for disruptions that occur on a kind of intercity transportation network. And some preliminary results that we can highlight here is just kind of looking at the Southwest United States in general. We can kind of see what the baseline conditions look like for freight and passenger traffic moving throughout this region. And then we can start to see what happens under various disruption scenarios. So what happens if a wildfire or flood closes off certain parts of this network? What might we expect the passengers or the drivers to do? And then can we also start to evaluate what various adaptation strategies might be able to do in terms of reducing the impacts of these disruptions? And so we can kind of see that here with some preliminary results where the disruption initially increases travel time up to 60%. But then looking at kind of what we call a robustness scenario where the impacted areas have some additional capacity put in place to minimize their impact, we can see that this travel time increase is more or less mitigated by these additional robustness approaches. So there's lots still to be developed here in terms of looking at different disruption scenarios. I definitely want to apply this to the Central Valley in California, in addition to kind of the Southwestern United States that I showed, and conduct some sensitivity analysis to help us discern some of the most important parameters. In the interest of time, unfortunately, I will kind of have to skip this section, but I'll touch on it at least in kind of the key takeaways. But yeah, just to kind of summarize what we've discussed today, the Anthropocene can not only be characterized by humans' influence on the natural environment, but also emergent properties such as non-stationarity, complexity, and interconnectedness. Given these kind of emergent properties, how we traditionally design and protect infrastructure is likely insufficient for the future. And then the analysis and design of our infrastructure systems in the context of the Anthropocene should strive to match the scale, scope, and complexity of the systems and problems being investigated. And just kind of just as a final slide here, moving forward, this is not these challenges are not something that any one researcher or even any one discipline is equipped to handle on their own. And instead, I think we need this kind of multi-tiered approach where we look to develop compatibility and modularity in our infrastructure systems. I think there's lots of lessons that can be learned from the ICT space in terms of how best to do that. Scenario planning and road mapping will become increasingly important. We should start thinking of resilience as a process rather than an outcome. So something like more of an action rather than a result. As we move more towards more towards smart systems and AI embedded in our physical systems, we really need to think about what the social and security implications of that are, and really start having maybe civil engineering students as at least novice cybersecurity specialists as well, because those two domains are increasingly combining and colliding. Plan for predictable and surprising events and outcomes. And our education system also needs to start embracing complexity and the idea of continued learning. So empowering our students to be able to think about these complexity and uncertainty and be comfortable with it and be equipped to kind of adapt to it as they are increasingly exposed to these various factors throughout their career. So I'll kind of leave this as a call to arms for all of us to kind of continue to think about and develop. I want to acknowledge all my collaborators on these endeavors. I certainly didn't do this work on my own, and I'm very appreciative for everyone's collaboration and contributions. And most importantly, thank you all for giving me the opportunity to speak to you today, to kind of introduce myself to CITRIS and to the UC community. I hope I maybe piqued your interest in some of these topics, and hopefully we can start having some fruitful conversations and collaborations on many of these efforts moving forward. So thank you very much.
Yeah, thank you so much, Sam, and thanks everyone to joining us today. We are at the top of the hour, so we will call the research exchange to a close. However, please do reach out to Sam either on LinkedIn, or you can find his contact information on the slide there at UC Merced, and we look forward to seeing all of you in the fall of 2021 under some different infrastructural conditions. So thanks so much, everybody. Have a nice day.